If only they knew all they needed was all of this. This is a precision factory in Germany.
Switch off the vacuum and the mixers. Then I have to vent it. And this will press down into the bucket. This is a Sigma mixer, and a Sigma mixer is I would say, the simplest way of making paste. Mixing Cryonaut Extreme takes roughly 20 hours in a Sigma mixer.
Wow. This is a tube of thermal paste. Thermal paste is used in nearly every modern electronic device for connecting heat sinks to semiconductors. Retail, 1 gram of this paste costs about $6, and we just made 1 gram of it in Thermal Grizzly's new factory in Hohen-Neuendorf, just outside of Berlin in Germany. So if a gram is $6 retail, this bucket contains 17 kilograms of paste, and this crucible contains thousands of dollars worth of liquid metal being made for more extreme cooling applications.
This is pure gallium.
Oh, cool.
It's the main component for liquid metal making. This is 1 kilogram of indium, and the value of this type of purity is about $400. So that means basically one of those bottles could be $8,000 US of value. Right. This stuff is a premix of zinc oxide at different particle sizes.
Okay. Do you ever feel like a drug dealer?
We fill very expensive material from like powders in bags into like 1 gram and charge a lot of money for it.
Right.
Yeah, that's right. If I sum up the business I'm doing, that's basically it.
Right. You've got it figured out. One thing that we've noticed is that Germans are proud of their manufacturing, because it seems like even the tools that manufacture the manufacturing are manufactured in Germany.
Which country do you think it comes from?
I'm gonna go with Germany. This is part 1 of a multi-part series touring factories in Germany. We've been to factories all over the world, including Taiwan, China, the US, and now we're making landfall in Europe. Let's get into Thermal Grizzly's thermal paste factory, mit Der8auer. Before that, this video is brought to you by the Height Y70 Touch Infinite. We previously reviewed the Height Y70 non-touch series and found its overall build quality to be good and competitive. Now, the Y70 Touch Infinite ships with a custom 14.9-inch IPS touchscreen with a 60Hz refresh rate. The screen connects to your system build and can be used as a showpiece on the angled corner front panel, displaying stats, music players, videos, and more. Height's entire Y70 series now also includes multiple new colors, like the Taro model that you're seeing here. Learn more at the link in the description below.
So we're moving into the chemical side of things, and this is what we call the paste and liquid metal room. And from just an overview point of things, we have on the left side everything that is required for liquid metal manufacturing. Everything that you can see here is related to paste making.
Cool.
So we have 2 different types of mixers for different types of pastes. And we have a so-called 3-roll mill.
Okay.
We will see what this does later. Then we have things we need for preparation of the paste, like getting the powders and mixing them. This is a station for quality check of liquid metal, mainly, or other materials for our HS testing. Then on the other side of the room, this is where we fill the stuff into syringes. Those stations are for liquid metal, currently 1 gram conductor node, 5 gram conductor node extreme. And this behind me, this would be for filling normal thermal paste into syringes. Yeah, we should move over to paste manufacturing because this will take quite some time.
Okay, let's do it.
It's kind of similar in terms of that you have to have all the stuff very under control. Apart from that, it's much more tricky. Like liquid metal making is actually quite simple from my point of view. Like now we've been using it for a long time, but making paste is really not as easy. Like the mixing is very complicated, and also the raw material stuff. We will actually show you how to make our new product, which is this.
Der8auer.
Yeah.
If you really break it down to like as simple as possible, I don't want to say elements because that has a specific chemistry meaning, but what are the base things that go into a paste?
A paste, you always have to have an oil, which is often referred to as matrix. Then any solid particle you want to add.
Okay.
And the very simple paste, the white ones you can find, they usually just have one ingredient, which is usually zinc oxide or aluminum oxide. But the more high-end you make it, the more different amount of particles you have to add, like different chemical elements and also different shapes. This machine right here is called a Sigma mixer.
Okay.
Usually you would not be able to do this because it would be mixed under vacuum. But as I told you earlier, this batch will not go for sale. Yeah.
Right.
So I prepared some protection glasses. Sometimes, you know, stuff. This one is for you.
Thank you.
This one is for you. We should make a paste.
Okay.
From scratch. This stuff is a premix of zinc oxide at different particle sizes. This is aluminium powder. So this is like nano size material.
If you ever get pulled over and you're transporting stuff like this, I'm gonna have to bail you out of jail.
Yeah.
I feel like everything you deal with is either dangerous or it looks questionable.
Yeah. What do you think happens when we order like 1 ton of this material and it arrives in white plastic bags?
Right.
Yeah. I'm always asking myself, like, what does the customs office do? Like, they reach this and they're like,
we got him, boss.
We got him.
You'd never guess how easy.
I wonder how many tests they run until they realize it's just nothing interesting.
Yeah.
The reason why you have to use different materials and different sizes is that we have to increase the filling rate, it's called, as high as possible. The filling rate means how much ratio of oil to solid particles we have.
Okay.
The higher the amount of solid particles, the higher the performance. That's just a rule of thumb. There's something to it, but that's the general rule.
Does that correlate with when a paste is hard to spread?
Yeah.
Okay.
Definitely. The spreading comes down to the viscosity of the oil and how much you fill it. So generally, if it's much harder to spread, it's usually higher performance. That is a bucket of something I wouldn't call thermal paste.
All right.
But it's an example of the filling rate. This one, you can see it's probably something you wouldn't...
Very viscous.
This paste right here has exactly the same ratio of filling rate. Like, this is much more liquid.
Wow, yeah.
It's much more liquid and they have the same filling rate. This is the paste we will do today.
Okay, cool.
Yeah, the aluminium powder is the most dangerous one in this regard. I told you earlier that you can have hydrogen being generated if you handle it. That's why we're using a glove box for this. The glove box can be filled with an inert gas as well to protect it. So we can handle everything inside and then take out just what we need.
Okay.
That will be the step.
Let's do it.
So just basically these 3 in the right composition and fill it into the machine.
Okay.
But before we do that, we have to wear even more protection gear.
Okay.
Just to be safe, because I told you do not want to breathe anything of this in. It's unlikely that something escapes, but you have to be cautious.
But, yeah.
This is the biggest pain, getting into the gloves. So what I'm doing, well, I already prepared one of them. That is the zinc oxide, which is this one. I had to get it out of the bag in the room. But what I'm doing now is using some of those glasses, setting this to 0, and then...
Okay, so you zero it out with the glass.
And what we want is, from this aluminium powder, we need about 15 to 1600 grams.
Okay.
And that's what I meant earlier, like this is the kind of step where you would just, if this was exposed to the ambient air, you would just introduce too much water and...
Do you currently have a gas in there?
Yeah.
Is that what this hose goes to?
Yeah.
I see.
It's always a little bit of a
Yeah.
The dirty process, but that's why we have the glove box. So we will use this machine for it, which is called a double planetary mixer. Depending on what kind of paste you're making, you have to have different types of blades, depending on the viscosity you're aiming for.
Cool.
So they exist in different blade shapes, like if it's lower or higher viscosity paste. And I will now get the aluminium powder and pour it into this bucket.
Okay.
Actually, I forgot something. I have to close the...
Oh, the bag?
Yeah.
I hope if anyone ever is upset that your paste is out of stock on Amazon, they understand it's because you're still putting the gloves on.
Yeah.
He's working on it.
Yeah. Yeah. Just for me, it's a lot of fun doing this stuff.
Yeah.
It's the best playground I could have ever imagined, you know.
Where were you when you were like trying your first mixes with the glove box?
I was still living at my parents' place.
Okay.
And they just had this in a.
Were they aware that the stuff you were dealing with could like blow up their house?
They stopped asking questions when I was 16 and I ordered like 200 liters of liquid nitrogen. They were like, "What the fuck?"
Yeah.
So.
Right. All right, so your bag's sealed. So now you're gonna retrieve the stuff you made.
Yeah. So now we just have to introduce the gas again later, but it's not needed
because you've opened the box, I guess.
Yeah. Now we just have to be careful not to pour it too fast, otherwise you will have too much dust. Want to avoid.
Just up in the air, you mean?
Yeah.
And then these are the blades here?
Yeah.
Okay.
Now we have to get the oil, but that is less dangerous. It has two basic functions. The one is mixing, and one is called dispersing. And with this type of motion, you can just mix any high viscosity paste. So that is needed when you're making a paste that is very thick. You need this type of blade. We have to switch on the chiller, which is actually a heater. Yeah. And this is heating up to 70 degrees Celsius.
Okay.
It is running water into the bucket in the wall around it.
Like around it.
To heat it up. The reason we're doing this is because in any of the raw materials you will find a lot of moisture. Since we're running in a very low vacuum, we just drop the evaporation point of the water. And this way we only have to heat it up to 70 degrees Celsius and getting all the water out.
Okay. Yeah, kind of like how a heat pipe works, I guess.
Yeah,
in the
exactly.
sense of reducing the boiling point, yeah.
So we're now pulling the bucket over here.
It's got a light in there too, so I guess that's so you can see it through your window.
Yeah. So if I now switch on the vacuum, we know it's working. Okay, that is good, because if it would have any holes, leaks, then you wouldn't be able to see it.
All right.
So if I now introduce the vacuum, you should see some bubbling and stuff.
Interesting to see the gauge dropping. So what are you looking for?
Especially in the early stage, you have to observe how it's mixing. That's what I meant. Like if you have a wrong ratio, or if something doesn't mix quite right, then it just can become hard in this stage. So you have to check if this is like if it's mixing properly, or if it's like piling up somewhere.
Is there any risk of damaging the equipment?
Yeah, that happened before. Like we had, you can see that here. So we were mixing one paste, and we had exactly this, that it hardened, and then it broke the scraper knife.
Oh wow, okay.
Because it was so hard that and the machine has a lot of power, so
it just crushes the
crushed
tool.
it. Yeah. Luckily, we have our own CNC manufacturing, so we just made our own.
Where does that read?
It reads the temperature of the water.
Okay.
And now we have the material temperature, that is the one that's sitting inside the paste, and we have the tank jacket where the water runs through. And just for safety, not safety, but for just to be sure that everything is gone moisture-wise, we heat it up to 70 degrees Celsius, so we have some room now.
Wow, yeah, cool.
So now I have to check how well it mixes, but it looks very good. This will now take a couple of hours to pre-mix. This is kind of the pre-mix, because we will still have to add the zinc oxide later. Okay. And the zinc oxide we have to add in 2 steps.
How many tubes does this end up filling? I mean, I know the tubes are different sizes.
This should be now, end weight will be roughly 3 kilogram.
Okay.
So it will be 3,000 1 gram syringes.
Okay, yeah. Is that the most common size?
Yeah, that's why we calculate in 1 gram syringes. Well, Duranout will be 2 gram syringes. People think this is like, why does the 1 gram cost $6? I mean, it's half of it goes to the seller, so there's already that, and then
upkeep.
We have to do all this, and especially the research. The making is not that quite expensive, but paying people for years to research stuff that's the real cost.
What is this?
This is our sample stub.
Okay.
This is for catching the raw material and taking it into the scanning electron microscope.
Okay. Do you have an SEM here?
Yes.
Cool.
That's what where we will go now.
So what are you doing here?
Just catching a sample of the aluminium powder. One of the key aspects of the performance of the paste will be the particle distribution. So we order this type of powder at a specific size. So for example, we tell them we need 10 micrometers, for example. And then it won't always, like, it will be a range. The 10 micrometer will be the D50 or D90 value, which means like the 50% or the 90% of the powder is this size, but then you have bigger and smaller particles as well.
Okay.
And it highly has a very big impact on your performance, how big and how small the rest of the particles is. And that's what we have to check.
Got it.
Yeah.
All right. So we're going upstairs.
Yeah, we now go to the first floor. First floor is where we have all the analysis tools. First floor is just dedicated towards R&D. The procedure is that we have to double check if this is what we ordered in terms of material and also shape. So that will be Eric's part. Eric is one of our R&D engineers, and he's, I would say, our specialist when it comes to operating this microscope. And he will.
What kind of microscope is it?
It's an optical microscope from Keyence. That's basically where my knowledge ends.
Walk me through what it is you're trying to do here. I guess you're lining it up.
First we want to check where the sample is. Yeah, we can go closer.
Is that a focus, I guess?
Yeah, and we can do a 3D. And then we can see almost the dimensions.
Is there like a zoom?
On the bottom right you can see it's 1,000 times magnified.
Okay.
And on the bottom right you also have this scale of 25 micrometers that gives you a perspective of the particle size. The problem is you can't really magnify more with an optical one. Like with an optical microscope, the limit is around at 1,000 or 2,000. If you just magnify further, you're at the limit of the wavelength of the light.
Okay.
You just can't really go further.
I see.
We have a laser beam here, and then we can see
cool.
material is 100% aluminum. Yeah.
So the laser shoots into the material and evaporates it. The wavelength that is emitted while doing so, that can give you the material. Because we should be able to see where it hit.
It's like a crater.
Yeah.
Wow, that's cool.
Yeah, that's where it was evaporated. So this would be like a 5 by 5 and then 25 micrometer distance. Like if you're going too deep, this is surely hitting the glue underneath. Because you can see oxygen, hydrogen, which is an indicator of some kind of glue. And then they see carbon, which is from the pad.
What actually comprises the SEM ultimately? Like what are the component parts of it?
The component parts, so we have the main unit, which is this, where we have the electron beam source from the top, going down into the chamber, which is the part on the bottom. Then we have multiple detectors. That's usually what you see bolted on SEMs from the side. That's depending on what kind of stuff you need.
So is that what these are?
Yes, those are
detectors?
Detectors, yeah.
Okay.
There would be a detector that is just purely for element detection. Then, for example, the one on the back is for secondary electron detection, it's called. So that's what you have as a so-called standard detector. Then you can have EBSD, which is a detector for like analyzing the crystal structure of a material.
Okay.
So yeah, I can show you in the operation for the powder. It's pretty nice to see. You can, for example, look at the shape and also material contrast, for example. We're not even allowed to touch this. Like we cannot move this around or anything. So, and we also cannot shut it down. Like we can operate mouse and keyboard and that's it.
Wow. Is that a licensing thing?
No, it's a warranty thing. On the back you can see a little bit more, but everything that's bolted on, like these things are detectors. The thing in the center on top is the electron source, so where it generates the electron beam. And then we have a ton of vacuum equipment. So underneath we have multiple stage vacuum pumps.
Okay.
The The big thing in the back is the first stage vacuum pump, and the second one is the so-called turbomolecular pump.
Yeah, so these are words I've heard before.
Yeah.
I didn't get an opportunity to ask. When I was with Intel, they talked about exactly what you're saying.
Yeah. Vacuum is very difficult in terms of what it is. Like,
Okay.
it might sound stupid, but it's basically a room without particles inside.
Okay.
You know, you're from a simple perspective, you might look at just a pump like, you know, sucking out air, for example. That only works until a certain degree, because you would have to have less particles in the one room for the others to move out.
Right.
A turbomolecular
It's
Turbo
yeah. How do you say it auf Deutsch?
Turbomolekularpumpe.
That's harder to say than in English. That's like way harder.
Okay.
Turbomolecular pump. All right.
So
yeah.
if we use a turbomolekularpumpe, then it looks like a turbine. And what you're essentially doing is you're waiting for the particles that are freely flowing in the room to randomly hit this turbine shape,
Okay.
and it traps it below. It is a very fast spinning blade, and all it's doing, it's waiting for randomly the particle to hit the surface and then just trapping it below and avoiding it to come back up.
The gloves are coming out. So is this for handling the sample?
Yeah.
Yes. Adhesive pad influences the result at all?
It will influence the result, but there's only so much you can do. We have to stick it somehow. We also have to make sure it's electrically conductive. Because we're looking at the surface with electrons. So the electrons are scanning across the surface, submitting secondary electrons, and that's what we're detecting. First, I will bend the chamber, and the chamber is now nitrogen being pumped slowly. You can hear the pump, the Turbomolecularpumpe.
Yeah. Is that what that is?
Yeah,
Okay.
that's what you hear. It's slowing down now that the nitrogen hits the blade.
Cool. Your warranty is void.
There was no sticker. That's our sample stage in the center, where we have multiple spots for multiple of those.
Oh, cool. Yeah.
With this type of sample, it's not really an issue. Just have to check that nothing collides anywhere. Have to press it a little bit. So what you can hear now is the first stage of the vacuum pump. That's the bigger one in the back. So on the bottom, we can see the pressure inside, which is an indication for the vacuum. That's also what I'm checking here in the system monitor to see if the vacuum is going as planned. So you're now looking at this sample stub. You can even see here the place where we just milled into with the laser.
Yeah.
That is very helpful right here, especially with bigger parts, because you can see that is, for example, one detector. And yeah, just trying not to crush anything.
What is it you're looking for? Like what's your, how are you determining what your final goal is?
The final goal is now to get an overview of the particle size distribution. So we will have to, in practical, we will have to zoom in onto a level where we can actually measure the particles and then move to certain areas and check for the particle size distribution and check if we can find anything that should not be there. It's a good example of what it shouldn't be. This is diamond dust. It's so small that even under 5,000 times magnification you can't really see it.
Right.
But there was one solid diamond piece in there that was 11 micrometers big, and that's just way too much. Then I'm inserting the detector, so you can see how this is coming in. So
do these tools have collision prevention on their own?
Yep. There is like a current, a voltage difference in between these, all these parts. So if I hit it, it will detect it. I know from experience, and it's not recommended. Here on the bottom, you see the scale of 20 micrometers. And just to get a reference, a human hair, if you do a cross-section of a human hair, it's about 60, sometimes 80. So a human hair would be about this size right now.
Right. So this is the image you took then?
No, that is the image that I took, right? Can properly see the particles. Also that they're not perfectly round as what you would expect. You have this stuff in here, which is all those tiny things will affect the performance of a thermal paste.
Do any of these look ideal to you? Like Do you want it to be uniformly small across the whole paste or mixed?
You want to have a very specific particle size distribution. So you want to have both bigger particles and smaller particles. Because you want to, if you squeeze the paste in between the cooler and the CPU, you want it to fill the gap. And the gap is not, like two flat lines. It's a lot of stuff here and there. I can probably show something like that as well. That is a copper surface after milling.
Oh, okay.
That is how it looks like on a water block from us.
Yeah.
So if you look at this, you might think like, wow, that's a shitty surface. But yeah, I mean, this is actually a quite nicely milled surface.
Okay.
But you can see, the milling cutter going across the surface, and that's how it will look like.
Right.
And what you want to achieve is that you want to fill all those tiny gaps with the paste and then fit it to the surface that's on top. And then you want to fill the bigger and the smaller gaps, and for that you just need different particle sizes.
Right. And I guess they kind of find their way into where they belong just from pressure.
Yeah, but that's what we usually, what I was doing here. So I was zooming in much more. This is almost 14,000 times magnified. The field of view here is 30 micrometers.
So you're from 0.28 or something microns up to 3.48?
Yeah, in this powder, yeah, but there's also different examples. If we look at this image, this is exactly as expected. The biggest particles here are maybe like 10 micrometers. And then you will find small ones, like if you zoom in all the way down, which should be this image right here. You can see this is 100,000 times magnified.
Wow.
So the field of view is 4 micrometers, and then you can find particles as small as 60 nanometers.
That's crazy.
Yeah. That is why this is only possible with the scanning electron microscope. We are back about 3 hours later.
It's going to be the best paste you've ever made.
Yeah. Check it in here. It looks much more uniform now.
Wow. Yeah. Last time I looked in there were big chunks still.
There's still a few, but they're almost gone. But what we have to do now is open it and add the zinc oxide.
Okay.
Switch off the vacuum and the mixers. Then I have to vent it.
Cool.
If you now think back how full this pot was when it was like this full maybe, and now it's maybe only a fourth full. It's because we got rid of all the air, anything that was in there, it's all gone. And now I will add the zinc oxide.
Okay.
So same procedure like whenever working with the stuff.
All right. So you're going to measure out a certain amount, I guess.
Yeah.
How much precision are you going for?
Just trying to hit the plus minus 1 gram.
Okay.
Especially if you already look at the mixer and that some stuff is stuck in there. It's only so much you can do, but it's still pretty controllable. It is easier to control the bigger you go in volume. So I have to do this in 2 steps.
Okay.
Because it would be too much at once. Otherwise you're risking this mixing dry out effect.
So what, you're going to move it a little bit and then do it again?
Yeah. It only takes like a minute to get this initial thing.
And then
then we can add the rest.
How do you know when it's ready?
It has to be a little bit like wet,
Yeah.
Like now, if you look inside, it just shouldn't look like, like a very dry dough, like from if you're making pizza, then. That's now basically the final composition.
Cool.
Now it has to mix.
How long does that run?
Roughly an hour.
Okay.
And then after we ran it through there, we have to take it out. So we will move the bucket to the left to the, not sure how this is called in English, but it's like moving out machine. So we can get the thermal paste out from the bottom. And then we have to grind it afterwards, which we will do on the 3-roll mill.
Got it. That's cool.
But this process is quite quick. It takes between 5 and 10 minutes.
Okay. So we'll do that at the end, I guess.
Yeah. And then after this one, there is the curing process, which is inside a vacuum chamber for 24 hours.
Okay.
So the entire process of making a batch like this takes around 2 days.
Wow. All right. From start to finish.
Yeah.
So in cooking shows, they do the thing where they already have it made in the oven and then they fake cook it. That's not what happened here. This was actually cooked thermal paste. He has been cooking it all day.
Yeah.
If we get a shot of the windows, it is now dark. What is the current status?
The current status is that it should be done, at least from the mixing part. We can now open it, and then we will be able to remove the thermal paste from the bucket, and then we should be ready for the grinding or milling step. Now you can see how the viscosity changed.
Yeah.
It's much more solid now, and you can also see that it's a much more even.
It does look like
structure.
A nice paste.
Yeah.
Do you scoop this stuff off the?
No.
Oh, okay.
It is a way to save cost or increase how much you have in the bucket, but you will see that up here there's still a bunch of unmixed particles.
Right.
And there's always a risk that I take them down. I scrape off the bottom things from
the stuff
here.
that's clearly good.
Yeah, that is clearly well mixed. Next is that I will call Eric to check if he's still here, because doing that with alone is a little bit. Magst du mir kurz beim Paste rausholen helfen? Perfekt, danke. Ja, genau. And it's a bit tricky especially because everything is heated up to 70 degrees Celsius, which is not that convenient. You can touch it for a couple of seconds, but everything here is extremely hot.
So is it actually the bucket going to come up?
This will press down into the bucket.
Oh, I see. Got it.
Yeah, that's just the air that's squeezing through. That's why I'm wearing safety glasses.
Yeah.
We now have to reach the point where all the air exited through here. And then we can close the valve here.
Oh, there it goes.
This anti-Newtonic fluid. So if you put a lot of pressure on it, it will just be hard.
Okay.
It wouldn't come out.
What's the capacity of that?
This is 1 liter, and due to the density being about 3, so it's about 3 kilograms. Still, even though it was mixed for 5-6 hours, you can still see a bunch of particles in here. Also, at this point, you shouldn't be fooled about how liquid it looks, because this is almost 70 degrees Celsius hot.
Oh yeah. Okay.
So once it cools down, it is a lot harder. That's also what we will see now. This is the milling or grinding. In this step, we push the paste through a tiny gap with a lot of force to have an even particle distribution. It changes the viscosity of the paste, and it gets rid of all those tiny spots. 3 mils is 2 steps. Right now, there's a gap in between those two. And in the first step, we just pour it in here, and then it will cycle between those 2 rolls.
Okay.
You will see that. That will take about 5 minutes. And then in the second step, the third roll is added. They spin at different speeds. And then the third roll exits the paste to the back. Also for this step, we have to cool. Like here, we have to heat it up.
Yeah.
For mixing, and here we have to cool it. Otherwise, we will run into this dry out issue.
Okay.
So this is much more critical, especially.
So do you cool the wheels?
Yeah, there's coolant running through. We cool it to. We have to stay below 30 degrees. Typically around room temperature is fine, especially if it's just this small step, small batch. It would probably be fine without cooling because it's so much mass. But yeah.
Okay.
Kannst du anschmeißen? Just switch on the chiller anyway. Don't wanna.
Yeah.
Fuck up the batch just because of being lazy, switch on the hydraulic system of this. And then, so there's 3 different operation modes. If I just turn this on right now, it is in the separation state. Separation means that all the wheels are apart from each other. We want to go to the mixing state, which is the first 2 touching. And then after the 5 minutes, we will go to the grinding and take it out to the back. And here we can observe the temperatures of the wheels, which are currently at about 22, which is ideal. The rolls they are parallel to each other. So that is what we can do with this. This is the gap control, where we push them. And then we have the roller pressure adjuster, which applies pressure to the rolls. Yeah. And these two are just to guide the paste that
keep it inside.
Keep it inside. Yeah. They have to be a little bit loose because we're now pushing the wheels together with the mixing. And now we will add the paste.
Kind of crazy, like just to see it all flattened into one plane.
Yeah, it's also very satisfying. If you do this, it's kind of it's a pretty satisfying thing. So what we have to check is that if we do this, that those particles will just be less.
You're talking about those like basically bubble looking.
Yeah, that
things?
was look. Sometimes if it's bubbles, that can happen as well. Bubbles are not really a problem because they will go out once we go to the vacuum
I guess
chamber.
you're looking for like these bumps, right?
Yeah,
okay.
like those bumps that come out. So we just have to grind it a little bit longer until most of them are gone. When people are thinking, why am I not doing YouTube videos? It's because I'm doing this.
What are you sitting in this year?
Yeah.
Yeah.
One day you're going to decide you've had enough of this industry and retire, and somewhere I'm going to find you running like an ice cream truck. You're just going to be doing this all day for ice cream.
You mean with the forbidden red ice cream?
Yeah. Yeah. Custard Grizzly.
Vielleicht kannst du gleich auf Grind machen, dann gehe ich rüber. So switching to Grind now.
Okay.
So now you can see, because this roll is spinning faster than this one, it takes off the paste from it.
Is there a stage after this?
Yeah, there can also, there will be the vacuum stage after this. Depending on the paste, you might also have to, like from this side, put it back in here and run this process multiple times.
Okay.
But it depends on the paste, on the particles, on the mixing process. And
looks like you've still got a lot in the middle there between those other two wheels.
Yeah.
So do you just keep running it till it's all out?
Yeah, we have to wait until all of this is gone.
Your best to your worst batch. How do you judge the variance?
We just do temperature testing, but I would say realistically, it can easily be like 2 degrees.
Okay.
On a CPU.
Yeah.
From the best to the worst, especially if you're making bigger batches, and once it goes to the filling process into the syringe, like the machine will start getting the paste from the top, and it will just be a different particle distribution on the top to the bottom. So it will just vary a bit. There's nothing we can do about it. Kannst du mir blaue Tücher geben? Also, it depends on how long you store it now, or if we directly fill it. Like if we would proceed to directly fill this into syringes, then the variance would be quite small.
Okay.
But the longer we wait now, the more separation will start, like separation of the particles and the oil. So now this has to go into vacuum chamber.
Oh, that's what this thing is.
And then you put the lid on it, to close this, switch on the vacuum pump, press it down a little bit, and then you can film from the top. Especially once it goes very down in pressure, you should be able to see some of the air coming out, like bubbles forming on top. So now we have to run this for maybe a minute. Doesn't have to run very long. And then we close the valve on the tank, and then it has to sit there for roughly 24 hours.
Okay.
Okay, there is one more thing we skipped earlier. I just forgot about it. It's cool, has been running for 7 hours now. That is a viscosity meter. That is one step that we do also for quality check. So we used a silicone oil that is meant to have a viscosity of 500.
Okay.
And we have to double check. Here we can see it's 522, which is perfectly within the tolerance of what we buy in terms of oil. But it is also one of the quality steps we do, at least when we get these buckets of oil. It's usually 25 liters.
Checking the supply as well.
Yeah, at least for the oil, we also check viscosity if it's correct. Also to control ourselves that we don't take the wrong bucket.
Right.
Finally stop that. 7 hours should be fine. All right, the same bucket that you just saw that we put into the vacuum chamber basically pulls out the thermal paste and then pumps it with currently 5 bars through this pipe in here and then here in this mechanism where we can...
Oh, wow, okay. So the paste comes down here?
Yeah.
So this fat tube, and then it gets pushed out into the syringe at the end?
Yeah. Yeah, usually it's... you dock to it, press dispensing. Now this is dispensing, you can see this is the time it takes for filling.
Cool.
This machine is close to 100,000 euros.
Wow, okay, yeah.
It's very specialized, it's made in Germany, which definitely adds to the price.
Yes. I see a scope and what looks like benchtop power supplies maybe?
Yeah.
What's that for?
We're currently working on automating our filling process. It's not quite ready yet, fully automated paste filling and liquid metal filling.
Oh, cool, okay.
Because the problem is that what we're doing is so far outside the typical stuff that we can't find a company that just offers this.
Yeah.
You can find machines for normal traditional paste filling, but this will be specific for liquid metal filling into syringes, to our standards.
Do large suppliers like those you've worked with in the past, do they already do stuff like this?
They manually fill it for liquid metal.
Okay. So to your knowledge, I mean, is there anyone who automatically fills liquid metal?
There is one in the US, as far as I know. Syringes will arrive here, and then we have this small motor that turns this into different steps. So we have one step for aligning the syringe, then we have one docking step where it's going to be filled, one for moving the cap on, then we will have another one here for laser engraving.
Oh, okay.
Because we want to, for the future, laser engrave every single syringe with a serial number.
That'd be good.
It's something you can't find anywhere else currently, and it's also a quality problem for us, like also for normal thermal paste. If something goes wrong on the paste or the tube itself, we can't really track it. We will now enter into our paste testing lab, paste and pads. We have two fully self-engineered, self-built testing machines.
This looks like heating elements into basically like a dummy heater.
Exactly.
Okay.
So that is the third iteration of this design that I made, and the base concept is just to mimic a CPU. We have 6 heating elements with 40 watt each, so 240 watts of heat. And we have
just cartridge heaters, basically?
Cartridge heaters, yeah.
Okay.
And they're controllable over this, which is also powered by Elmore.
Okay, yeah.
It's a TPC. He designed it for us, so we have fully controllable outputs that are temperature controlled. So we have multiple temperature sensors in there, 2 for control, 2 for measurement. And then we can program the outputs if we want to for specific heat output, or just for normal testing, we would go full out. We could just enable this, and then all of the 6 outputs would run the 40 watts each.
Looks like your pump turned on too with that.
Yeah.
So let's go big picture. What are you trying to actually do with this setup?
We want to just simulate what the customer would experience. You have your 2 pieces. We have our CPU. It's a piece of copper, nickel plated. It has exactly the same roughness as a current Intel CPU. And this is basically just an enormous water block. And we press it down with a controlled force. And then we also have a sensor here that can check the height of the layer in between both surfaces. But what we measure is with this, the temperature delta between both surfaces.
Okay.
This is extremely accurate. And I think all of this also costs about 30,000 euros.
Yeah.
So, but the thing is, for us, relevant is the delta between the surfaces, because this is exactly what a customer will have. The customer won't care if it's a high conductivity or not, because apart from the conductivity, there is the interface resistance, so the contact resistance between the thermal paste and this. Then the layer thickness plays an important role. Then how the heat spreads within the material. And then you have the outside factors such as surface area and how much heat you're pumping through it.
Is endurance a separate consideration?
Yeah.
Okay.
So endurance, that is also an interesting factor. For that, you would do temperature cycle testing. And for temperature cycle testing, you would, for example, heat it up from 20 to 80 degrees and do that maybe 5,000 times. And that's how you simulate aging. And that's what we can do with these. And then that one for paste and that one for pads, because the one for pads can have adjustable height. That is, I think, quite interesting maybe. For this kind of dummy heater, it's also important to have the right surface geometry.
Yeah.
Because it has a huge impact on the aging. It completely ages different if you have it on a GPU versus, let's say, this is the same material. It's nickel-plated copper, and it expands and shrinks roughly the same.
Yeah.
But this, being silicon, it will act completely different. So if we replace the heater on here with this one, the aging will just look completely different.
Interesting. Okay.
Yeah.
Because the silicon itself is not powered. Are you actually putting that piece in there, and then is it just conducting through whatever?
It's just conducting the heat through the.
So your goal then is you're heating it externally. You're heating the silicon piece externally, but you're still getting the characteristics of the silicon.
It is very close to it because this is an actual NVIDIA GPU. It's a
GA102.
Yeah. So it was like 3090.
I think so.
Yeah. And it is an actual chip from a GPU that we took off, and we grinded it down to remove the layer that contained the
BGA, I guess.
Not only the BGA but also the transistors.
Okay.
So it's just purely the silicon, and then it's bonded on here. And basically, I mean, we're simulating the transistor layer generating heat. So it's very similar. And
it's actually meaningfully different than just doing a copper plate?
It's completely different.
Okay.
Completely different, yeah.
Cool.
Especially if you change between traditional paste and liquid metal. So the thing is here, we can also offer to especially customers from us who want to buy liquid metal, and they want to know, for example, on a notebook, how does it act and age? If you go back to the TIM tester you were thinking about to buy, these kind of TIM testers, they often simulate the aging by moving the stencil up and down. Which is fair enough, it is close to it, but it's not the reality. The reality has different factors to it, like completely different surface geometry.
Right.
And that's something you just can't simulate with any of these devices.
Yeah.
That's why we made our own ones.
And I do have more questions about it, but also you want to do something on your channel, it sounds like. So we'll do that plug where we'll try and line it up where hopefully we just post at the same time. So if you're seeing this video, he should have something up, and he'll be able to talk more about
I will explain all more details about like how does the layer thickness matter, and showing how we test this.
Well, there'll be more in his video on the channel Der8auer or Der8auer EN. So check that out. To kind of recap, we've been here for about 8 hours. It's a lot that goes into a.
The thing is, because we're a small company, we don't have 100 people working here, so we also have to check how we delegate our people and try to just make one thing at once and just be more cost efficient, because we're already quite expensive, which is the nature of running this, paying for all this, paying for the people
in Germany.
In Germany, and we somehow have to fight mainly with Asian production, obviously. Well, basically just with Asian production, I think. I think there's no other company in our industry that manufactures anything themselves. Like any of our competitors don't have their own manufacturing.
For paste, not that I know of, but everything I know of is done in China for the most part. So you target efficiency. What is the actual staff count that's sort of hands-on with this stuff? Because I know there's like marketing and accounting and whatever.
So if we just purely production focus, it's about 5 people.
Wow, okay.
Yeah. And then, but that's the people here. And then I told you we have a couple of people that work remote for also filling liquid metal by hand, because we don't have enough capacity to do all that. So we have a few people there, then people managing everything, buying raw materials and all that. So I would say it's maybe like 6 to 8 people just for the production themselves. Okay. It's small.
Yeah. This was a long day learning about how thermal paste is made, and the science and precision that goes into it is a lot more than we expected coming here. We have multiple additional videos coming out from our Germany factory tours. Up next, we saw Watercool, the water block manufacturer also based in Germany, and we saw Thermal Grizzly's liquid metal factory process and its CNC and water block manufacturing processes. If you want to learn more about this type of content, go to our factory tours playlist, where you can see factories from all around the world and how they work with what they make. We self-fund all of this content, so to help us continue to pay for these trips and all of the editing and production time that these videos take, Go to store.gamersnexus.net and grab something like one of our PC building anti-static mod mats, our project and soldering high heat resistant silicone solder mats, t-shirts, dice, and more. Subscribe for more as always. Go to patreon.com/gamersnexus to throw a few bucks our way to support this type of content. Check out Der8auer's companion upload for this video, and we'll see you all next time. Das Loch nicht zum Auern or Hartung.
Yeah, it says, do not close this hole. That's actually, I didn't see that for a long time. That I put this up there when we were renovating the building.
Okay.
So the construction workers would know not to close this.
Yeah.
Because
I had the same problem when we renovated our building.